Hey guys, in this video we're going to cover what recursive binary search is. So based on the binary search that I provided in the previous video, the link is given on the top right corner of this video, and in that video we had learned that using the while loop we keep iterating over the left and right values and keep altering them inside the while loop until our mid target is achieved, right? So in this video we're going to achieve the same thing but using a recursive algorithm, right? And everything, the way that we take the input from the user is exactly the same as it was in the previous video. So I recommend that you check the previous video out first to understand how we take the input from the user in a space separated list, and we're going to split them, map them with each string, convert them into an integer, and convert the entire mapped object into a list. So we're going to understand that in the previous video, and I'm going to briefly go through that in this video as well. If you haven't watched the previous video, then we are going to conduct the recursive binary search, which is the main part of this video, right? So one thing that I would like to clarify is in this particular diagram that we see on the right hand side, this list that we can see, it keeps reducing, right? It keeps halving. As we know that binary search, it keeps halving, and by doing that our search space becomes smaller and smaller. So on doing that, when our search space becomes smaller, the search becomes narrower to find, and when it becomes narrower it becomes easier and less time taking. So the time complexity in that case becomes O of 1, right? When that is when our element is right in the middle. So that performs or outperforms O of log n. Like for example, if our element was on the corner of that list, right? Because it would keep halving until that particular element would be found. So at first, this is the entire list. So the range starts from 0 to 7. The second iteration, if our numbers on the right hand side, our list would reduce to this. That means that is only 4 elements left. And then finally, our mid target is going to change accordingly. Initially, our mid target was 45, that is index 3, because we have 7 here, 7 values. So 7 floor divided by 2, that means that gives us 3. So the index 3 would be the mid value. So when that changes to when our list also changes, so our mid target is going to be 67, that is index 5, right? So like that, if we keep going on, our search space becomes smaller and it reduces with uh, this recursion, right? So when it reduces, our search space becomes narrow and it's easier to find the target level. So that is one thing. And in this diagram that we see right here in front of us, it is the call stack. So the first call that we are sending is 0 to 7, right, which is the left and right values, and the target will remain the same as it is for each call stack. And we are also going to send the list, right? So on doing that, before I come to that, I would like to first explain the part where we are taking the user input. So what happens here is we have a class recursive binary search, and we have created a object of the type recursive binary search. I use that object to return the values into a tuple, that is numbers and target. That is what the content of the tuple is. So inside user input, we have split the values. So this is the entire string that we have. So what we're going to do here, the split function is going to split this entire search or rather this entire list or entire string into separate values, right, from the spaces. So it's going to be a multiple strings that we're going to get. So that is what split is going to do. Thereafter, we're going to use the map function, and map function has two parameters. That is, the first parameter is integer, that is the parameter that we're going to use to convert this each string into, right? So it's going to convert each string into an integer. So map object, what is going to do is going to return us an object. So what map is going to do, is going to convert each string value into an integer. Okay, and that is going to return us this entire map object of integers, right? And that is what we're going to convert into a list, and that in turn is what we're going to store in numbers. So we have numbers now from the user, and we also are going to get the target, which we are typecasting as well as using the type inference. That target is of type integer, and we're going to store that in the variable target, and we're going to return the numbers, which is going to be the list, whether be it sorted or unsorted, and we're going to return that as a tuple, which is going to be a list of integers, right? Which that is going to be numbers, and is going to be an tuple is also going to have an integer, which is going to be the target. So that we're going to store in numbers and target. Thereafter, we have called the isSorted method using the object, and we have passed the numbers list that we receive from the tuple. So when we're going to receive that numbers back from isSorted method, this is undoubtedly going to be the sorted array, right? So isSorted is basically going to be responsible for checking whether it is sorted or not. If it is not, it will just sort using the Tim sort algorithm, as I had explained in the previous video. I highly recommend that you watch the previous video before we come to this, because explaining this all over again is a little time consuming. So ultimately what we're trying to do here is we are sorting this. If we get that the particular number, the index that we have, from that index that we have, if it is greater than the next number, that means that if it is not in ascending order, that means the previous number is greater than the next number, then that means that it is not in ascending order. And if it is not, we just sort it and we return the numbers, the list, right? And if it is already sorted, we just return the numbers anyhow. Thereafter, we call the recursive binary search, and we pass numbers, which is going to be the list, the sorted list, right? The target, which I say would be 56, and that is according to what I have did the dry run or the algorithm on the right hand side with the number 56 as the target, right? And we're going to have the left value as 0 to start with, and the right value as 7, because length of numbers, that is numbers, is going to be 8, right? Because we have 8 values here, and length of 8 numbers minus 1, that is going to give us 7, right? Because we have started from the left index as 0. So 0 to 7 is 8 integers, right? And ultimately whatever result that we get back as an integer, we're going to store it in the result, and that is what we're going to print out later. Okay, so what happens inside recursive binary search when we call this, right? And we have the first call method, that is the first stack, that the first call that we have, that is we are sending the list, the target, which is 56. We're going to start with the left value as 0 and the right value as 7, as said, right? And I'm going to come back to the second call as soon as we progress. So what happens here is, when we are getting the numbers, we are getting the target, and what we're going to use mostly inside this recursive loop is the left and right numbers. So we're going to alter the left and right until we find the mid target. So the left gives us 0 and the right gives us 7. So the left, which is 0, it checks whether it is greater than 7 or not. It is not, right? So this is not fulfilled, so it does not go inside this. So return minus 1 is not fulfilled, so it does not return minus 1. So what happens after that is it stores the mid value, right? So it calculates the mid value using the left and right. So the left and right, that is 0 and 7 divided by 2, that gives us 3, right? So we use that index 3, that is going to give us 45. So I have taken this list A, and here the numbers is equivalent to A. I have taken this variable name for the list as A because it is shorter and more concise. Writing numbers inside this is more tedious, so I chose the easier option. So the thing is that when we have the mid value as 3, we're going to use that value and we're going to get 45, right, as a mid value, as a mid target, and we're going to check that if that is a target or not. So numbers mid, that is numbers of the index 3, right, that is 45, whether it is equal to the target. So our target was what, 56, right? And I don't think I have written that anywhere down, so I just write it down here just in case it's clear. And then we return mid, right? So we are not returning mid because it is not equal. So 45 is not equal to 56, correct? So what we do then is we come into the else if block and we check if that numbers made is less than the target. That means if 45 is less than 56, which is correct, so it executes this function again. So now we come into a recursive loop, right? Because it is calling this function, which is the name of the function itself, again. So we're going to send numbers again, the target, and we're going to change the left value and the right value is going to remain as is. Okay, so what we're going to do is when we call numbers target and we're going to change that left value. So what happens now when we change the left value? I have circled 4 here, and that's because earlier it was 0, right? The left value was 0. And how did we get 4 here? Is when we had the mid value as 3. So we are taking mid plus 1. We are changing the left value as mid plus 1, right? Because this is the third parameter, and here also it is the third parameter. So the left value, the parameters, the order of the parameters need to be the same as how you call the function, right? So that carries a lot of weight. So when the left value is keeping on changing from 0 to mid plus 1, that is going to give us 3 plus 1, which is 4, right? That's how we get the number 4 right here, the left value. And the right value is going to remain as is, which is 7. So what we have done here is the range becomes from 0 to 7 to 4 to 7. So earlier it was this entire range, okay? And then the second call stack, that is in the second iteration, when the call stack, when the function was called the second time, we have broken that entire list into half the list. So we are halving it basically. So earlier we had this entire list, now we just have half. So I'm just using this entire thing to hide half the list. So we have from index 4 to index 8. So we're not going to check on this side, right? We're not going to check on the left side of this list because our search target is not containing on the left side, it's containing on the right side, because we already checked if it is equal or if it is less than. So since it was less than, that means it has to be on the right side, right? Because 45 is less than 56, right? So we eliminate the left side of the list. Now since it has become half, we now change the mid value again, right? So what is going to be the mid value of 4? If it was 5 integers, it would have been easier because the third number would have, we would have chosen that as a mid value. But since it is a 4, we are taking a floor value, right? So we are going to calculate the floor value of left plus right again. Alright, so first we're going to check if left is greater than right or not. So since 4 is not greater than 7, this is the second call stack, the second iteration. 4 is not going to be greater than 7, right? So what we're going to do is we're going to come out of that if loop or if statement, and we're going to check, we're going to use the mid value, that is going to be 4 plus 7 floor divided by 2, that is going to give us 5, right? So we're going to use this index 5, that is going to give us 67, right? So is that 67, that is that number in that index, equal to the target? That means is 67 equal to 56? No, right? So we're going to check if it is less than the target. So if it is less than, which is currently not the case, we go into the else block. So if it is not, 67 wasn't less than the target, right? So this is not executed. Now we're going to return this recursive call, right? So when we return this recursive call, this is the third recursive call made right now, right? So we're going to come out of this and we're going to get into the third loop. So what happens here is we send the numbers and target again. The left is going to remain as is, right? Because in this case it is not on the right side but on the left side of this entire list, right? I have already hidden this, so we now have 4, right? But since 67 is greater than 56, we are not considering the right side anymore, right? So now our right value is going to change. So instead of 7, which earlier it was 7, instead of 7, now the right value is going to change to 4. And how it is becoming 4 is when we reduce this mid value from 5. Earlier it was 5, right? The mid value was 5 in the second iteration. We're going to reduce that by -1, so that becomes 4. Okay, and the left value remains as is. The left value will remain as is. So earlier it was 4, and the third call stack is going to remain as is, right? So when we have the left and right, so we're going to call that function again with the left and the right values. And what happens now is we're going to get the left value as 4 on the third iteration and the right value as 4 again. So we're going to check if left is greater than the right. That means if 4 is greater than 4, it's not. It is equal, right? And that condition was not here. So it's not going to get inside this again. And instead it's going to come out and calculate the mid value. So 4 plus 4 floor divided by 2, that's going to give us 2, right? Right here. 4 plus 4 floor divided by 2, right? Sorry, that's going to give us 4, right? Because 4 plus 4, that's 8. 8 floor divided by 2 is going to give us 4. So that means we're going to check with index 4, right? And that is going to give us 56 ultimately. So with that, we're going to take that integer and we're going to check that with the target. And if they're equal, then we just return the mid value, right? So that does give us 56 because the target was 56 and that matches with the index 4, which is the mid value at this moment, right? And since it is checking that they are equal, so we are returning from the function right here. So this entire block on the third iteration does not execute, right? Ultimately, when we have found the number, this is the last execution statement in this function, right? The recursive call is not made anymore. So on the third call, we're going to get the list. We're going to get the target 56, the left value and the right value, okay? And that is going to return us a value 4, because after the third call stack, or rather on the third call stack, we're going to get a value 4, right? Because while the third stack is going on, we are going to check that the value is equal to the target. So we're going to return 4 in this statement itself. We're not going to execute this. So we are not going to have a call here. There's not going to be a call 4, right? So right then and there is going to return 4 back to call 3, and from call 3 is going to go to call 2, and call 2 is going to return that to the first call. That means when it was called right here inside the main function method, right? So when we get that during the backtracking, that means what happens here is when this entire call stack is made, what happens is during the forward traversal, right, when the first call is being made, then the second call is being made, and the third call is being made. So recursion is building the function calls and it's reducing the problem, right? So that's what in the first traversal, that's what happens, right? We are not going to return the value because we haven't found that value yet. This is what normally happens. And during backtracking, the recursion is returning the values upward, right? It's returning the values upward. So it's building the call stacks, and while backtracking, it's the values are going upward, right? From call 3 to call 2, call 2 back to call 1. But for recursive binary search specifically, the actual searching works happen when during the forward traversal, right? So during the forward traversal, we already found that the value is equal, right? So while we were searching and before we had backtracked, before we had actually returned this mid value back to this function where it was called, we had already found, by then we had already found the search, right? And it was equal to the target. And if it was equal to the target, that is when we return the value 4, right? So that would mean that backtracking mostly just propagates or sends the result upward unchanged, right? So 4 is remaining as 4. It is not changed and it propagates upward, right? So the mid value doesn't change while backtracking. And this is very important and different from problems like factorial or Fibonacci, if you have done that before, and tree depth first search, permutations, and maze traversal. So that's where the real computation often happens during backtracking, right? But in binary search, it's much simpler. So the search is found much earlier before the backtracking is done, right? So that is it for this video. I think we have covered recursive binary search as well as the normal while loop binary search, and we learn how recursive binary search works internally, how recursion keeps reducing the search space into halves, how the call stack grows, right? In this, it keeps reducing, the list keeps reducing, and how the call stack grows in the first traversal and during function calls, and how the values return back during the backtracking, right? It's unchanged. So the biggest takeaway here is the recursion is not magic. It's simply a function calling itself with a smaller problem until a base condition stops the process. So until you understand the forward traversal and the backtracking flow properly, recursion becomes much easier to visualize and implement. So till then, keep practicing, and I'll see you on the next one.